So, what if we told you that some of the most stubborn, seemingly unsolvable mathematical problems might not actually be unsolvable after all?
Right.
That there's maybe a new way, a new path to finding exact answers where before we really could only guess. Today we're doing a deep dive into Ezouidi's theorem. It's a pretty groundbreaking method that's really shaking up how we approach these high degree polynomials.
Yeah, and our mission today is really to explore how this theorem gives us exact symbolic solutions. We're not just talking about improving on, say, numerical approximation.
Which have their limits.
Absolutely. This sort of redefines the whole game. It even challenges some, long-held beliefs in algebra, particularly related to Abel's theorem. It's about unlocking possibilities we didn't think were
The whole
there.
game. And to
It
really
even
show what this
challenges
thing can
some,
do, we're going to tackle
long-held
a
beliefs in
pretty
algebra.
formidable challenge, a 14th degree polynomial.
Oh yeah, that's a big one.
It is. And
Yeah.
you'll see why this isn't just like an academic exercise. It's actually a really significant step forward, especially for anyone who relies on precise mathematical models.
Definitely.
Okay, so let's unpack this specific problem. The polynomial we're looking at today is, well, it's a beast.
It really is.
Imagine something so long, so intricate, it'd almost fill a blackboard if you wrote it all out.
Yeah, pretty much.
It's a 14th degree equation. Just that number, 14, as the highest power of x.
Yeah.
That tells you right away how difficult this is for traditional methods.
It's the kind of thing that, usually makes mathematicians kind of groan.
Right. Throw up their hands.
And if you think about the classical approaches, their limitations become super clear here. For decades facing these kinds of equations, we often leaned on numerical methods. Newton's method is a famous one.
Okay.
But these methods are essentially like making a really, really educated guess. They give approximations.
Close, but not exact.
Exactly. And they're prone to rounding errors. They just can't guarantee exact values, especially when you get to these higher degree polynomials where, tiny errors can snowball.
So it's like trying to see something clearly through, I don't know, a bit of fog. You get the shape, but not the sharp details.
That's a great analogy. And it goes deeper too. You mentioned classical algebra. There's something called Abel's theorem.
Right, I've heard of that.
It basically states that certain polynomials, specifically degree 5 and higher, just cannot be solved using what we call radicals.
Like square roots, cube roots, that kind of thing.
Exactly, those simple nth roots. It's been a sort of foundational belief that some equations just don't yield to those standard tools. But Ezouidi's theorem, it fundamentally challenges that idea.
How so?
It claims to sort of sidestep those classical limitations. It demonstrates that even polynomials, which do have roots that can be expressed with radicals, can be solved exactly using its method. It really makes you question what we thought was possible.
Okay, so let me recap. Traditional methods, they often fail outright or they give you these fuzzy, imprecise results. But Ezouidi's theorem arrives and promises precise, solvable roots for things we might have otherwise called unsolvable. That's a huge shift.
It really is.
And you mentioned something specific about our polynomial.
Yes. A surprising little fact about this particular 14th degree monster, x equals 1 is actually a root.
Okay, so plug in 1, you get 0.
Right. But it's a root of multiplicity too, meaning it sort of counts twice or has this double impact. And Ezouidi's theorem is clever enough to identify.
Interesting. So that's kind of a foothold.
Exactly.
Yeah.
And this is where the theorem really starts to shine as this promising alternative. Its core idea is to break down the polynomial, but not into approximations. It breaks it down into symbolic parts.
Symbolic parts.
Right.
What does that mean practically?
Well, think of it like, instead of just guessing what a giant machine does, you systematically take it apart piece by piece. You figure out how each component works and fits together.
Okay.
It uses a recursive process. Step-by-step calculations that find the exact values, completely avoiding those approximation errors we talked about.
Right, the rounding errors.
Yeah. There's a general formula involved. It looks quite complex on paper, but it's essentially the engine driving this symbolic breakdown. It's a systematic way to compute these precise values.
And how does it apply here? It uses coefficients from the original polynomial, right?
Yes, exactly. The method expresses the polynomial using these new symbolic coefficients. You can call them Unbelows coefficients, maybe. And they are calculated recursively, step by step, based on the original coefficients of our 14th degree polynomial, the 9 to 14, the 91, the 9 to 364, and so on.
Okay, so it's transforming the problem.
Precisely. And here's the truly fascinating part for this specific polynomial. When you run through those recursive calculations, something remarkable happens.
Okay.
Almost all of those symbolic coefficients, they turn out to be 0.
Wait, really? Most of them?
Yeah, huge number of them. Out of the 14 potential symbolic coefficients that define this transformed polynomial, only 2 are non-zero.
Wow. Okay, that sounds like a massive simplification.
It is a massive simplification.
Okay.
This is where the cleverness of the theorem really pays off. It just blows classical approaches out of the water at this stage.
So how does that work? How does it simplify?
Well, because almost all those Sansi's coefficients are 0, that original terrifyingly long 14th degree polynomial, it just collapses.
Collapses how?
It becomes much, much simpler. It turns into an equation that basically looks like x raised to the power of 14 minus one of those non-zeros coefficients times x raised to the power of 7 plus the other non-zeros coefficient equals 0.
Okay, hang on. X to the 14, x to the 7, and a constant term.
Exactly.
That looks familiar, like a quadratic equation.
Precisely. It might still sound a bit complex, but the incredible thing is you can view this simplified form as a simple quadratic equation.
Yeah.
But the variable isn't x, it's x to the power of 7/5.
Whoa, okay. So you've effectively reduced a degree 14 problem down to solving a quadratic in terms of x to the 7.
That's the magic step.
That's pretty remarkable. How often do you see that kind of simplification with these really high degree polynomials using, other methods?
Basically never. Not with traditional methods. They just don't work that way. And once you have that quadratic form in terms of by 7,
You could just use the good old quadratic formula?
you got it. You solve for by 7 using the formula we all learned in high school. And then to find x itself, you just take the 7th root of those solutions for by 7.
Okay.
And the crucial part here, and this is really key, is that these solutions you get, they are not approximations.
Right.
They are precise, exact symbolic expressions. They might involve complex numbers, often expressed using complex exponentials, but they are exact. This is a direct result of the theorem's careful recursive steps. No guesswork involved.
So you end up with these formulas for the roots, not just numbers with decimal points.
Exactly. Formulas involving potentially roots and complex exponentials, but mathematically precise formulas. Now, this obviously raises a big question. How do we know these are really the right answers? How do we verify them?
Yeah, especially with something so complex initially.
Well, unlike numerical methods, which always carry those little rounding errors and only give approximations, these exact symbolic roots can be plugged back into the original super long 14th degree polynomial.
The beast we started with.
The beast itself. And when you do that calculation symbolically, the result isn't close to 0. It's exactly 0.
Wow.
We use symbolic.